All right, so we left off with spin quantum numbers. So spin quantum number, m sub s, describes the two possible states. M sub s can be plus 1/2 or minus 1/2. Any electron, regardless of the atomic orbital it's located in, can only have one of these two values of the spin quantum number. So here we see two different electrons. In order for two different electrons to occupy the same orbital, they have to have opposite spins. So their m sub s value for the first electron is going to be plus 1/2. For the second would be minus 1/2. All right, so that's the only way they can occupy the same orbital space. All right, so we need to learn about the Pauli exclusion principle. So we've already talked about the four quantum numbers N, L, m sub L, and m sub s. So Wolfgang Pauli, an Australian physicist, formulated a general principle. It's referred to as the Pauli exclusion principle. It says no two electrons in the same atom can have exactly the same set of all four quantum numbers. So electrons can share the same orbital. It has the same set of quantum numbers N, L, and m sub L. So if I have two different electrons that are in the same orbital, they can have the same N, L, and m sub L values. But they have to have different m sub s values. Okay. So since the spin quantum number can only have two values, plus or minus 1/2, no more than two electrons can occupy the same orbital. If two electrons are located in the same orbital, they must have opposite spins. So to summarize quantum numbers, we know N is referred to as the principal quantum number. Okay, it means it has a certain shell or a certain row on the periodic table. Okay, allowed values for N, +1, +2, +3, all the way up to +7 on the periodic table, but technically you can go past 7 because theoretically if there are other planets out there, and theoretically there could be more elements than what we have on our planet, and so mathematically you can have a quantum number greater than 7 and associated L and m sub L and m sub s values for those as well. So the quantum number tells us basically the energy value for that electron in that orbital. Angular momentum quantum number L, okay, is the subshell. It's the shape of the orbital. So we know S subshells have a spherical shape. P subshells have like a dumbbell shape. D and F are more complicated. Okay, so how do you find the L value? The angular momentum quantum number? You look at the N value. You start with the N value. If it has an N value of 4, N minus 1, so 4 minus 1 would be 3. And so your L values would be 3, 2, 1, and 0. Okay, so you go all the way from whatever your N minus 1 value is, all the way to 0, and list those values out, and that's your angular momentum quantum number. So your magnetic quantum number, m sub L, okay, is the orientation of the orbital. So that's equal to negative L to 0 to positive L, okay, including 0. And then your m sub s is your quantum number that is associated with the spin. So it can be positive 1/2 or negative 1/2. So it's basically the direction of the spinning of the electron in that orbital. You can have a maximum of just 2 electrons in an orbital. All right, so before we go on, I have a couple examples to show you. The first one here is example 6.6. I'm going to bring that up. Here, when we were talking about particles acting as waves, okay, It says if an electron travels with a certain velocity 1 times 10 to the 7th meters per second and has a mass of 9.109 times 10 to the negative 28 grams, what is its wavelength? So we can calculate the wavelength of an electron by first knowing our formula here. So the wavelength is equals to Planck's constant divided by the momentum. Momentum is equal to the mass times the velocity of the particle. Okay, so here we have the velocity in meters per second. We have the mass, and so Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. And so we plug that into our formula, and we get a wavelength of 7.274 times 10 to the negative 11th meters. Okay, so for these types of problems, pretty simplified. You just plug into the equation to solve for the variable you're looking for. The next problem, here's 6.7, is dealing with quantum numbers. Okay, so let me read the question because it's a kind of a complicated question here. It says indicate the number of subshells, the number of orbitals in each subshell, and the value of L and M sub L for the orbitals in the N is equal to 4 shell of an atom. All right, so we're really talking about N equal to 4. So the electrons associated with that energy value. So they're asking a bunch of different things. Okay, they're asking for the number of subshells, number of orbitals in each subshell, the L value, and the M sub L value. So they told us the quantum number, N is equal to 4. Okay, so what I'd first like to do is find L and M sub L. And then once I know that, then I can find these other things. All right, so if N is equal to 4, L is equal to what? So we know L is equal to N minus 1, or 4 minus 1, which is 3. And with L, we know we have to go all the way to 0, right? So 3, 2, 1, 0. And what do those numbers represent? We know those numbers represent the subshells, right? We know when L is 0, S, it's an S subshell. This is S. When L is 1, that's a P subshell. When L is 2, that's a D subshell. When L is 3, that's the F subshell. Okay. So that's what I have written here. So we have S, we have a P subshell, we have a D subshell, and we have an F subshell. Now that's not always the case. Okay. I'm going to give you an example. I'm going to do this example first. But actually, let me veer off a little bit. What if N was equal to 1? L is equal to N minus 1. So 1 minus 1 is 0. So we only have one S subshell at N equal to 1. Now, does that make sense? Let me show you the periodic table here. The first, N equal 1, that's the first row in the periodic table, right? These are both color-coded blue. I know this isn't color-coded for you based off subshells, but if you remember, both of them are blue. They're both S subshells. There's only an S subshell in the first energy level. There's no such thing as a P subshell on the first energy level because it's on the second, not on the first. Okay, so does that kind of make sense to you? Now let's go. Now we just figured out that with an N equal to 4, we have S, P, D, and F. All right, so if we look here, we have S. Actually, let me go back to the color-coded one because this might be confusing. All right, so N equal to 4. So we have S here, we have P, we have D, and we have F, okay? The first row in the F block is a 4. So an N equal to 4. So you have S, P, D, and F for a quantum number of 4, energy level of 4. So that just verifies what we found here by plugging in the equations there. All right, so let's go back to the problem now. All right, so get rid of that. All right, so I found my L values here for what I'm talking about here. So now I need to find my M sub L value. Okay, so M sub L is negative L to 0 to positive L. So for L equal to 3, okay, L equal to 3, it's negative 3, negative 2, negative 1, 0, 1, 2, 3. For L equal to 2, it's negative 2, negative 1, 0, 1, and 2. For L equal to 1, it's negative 1, 0, and 1. For L equal to 0, it's 0. All right, so we know L equal to 0 is S, right? So, isn't there one number there? That represents one orbital. S has one orbital. See how there's 3 numbers here? 1, 2, 3. There are 3 orbitals. When L is equal to 1, isn't that P subshell? There are 3 orbitals in the P subshell. See that? L equal to 2. There are 5 numbers there. Each number represents an orientation, right? Remember, this is the magnetic, the spin, the orientation of the orbital. So there are 5 numbers there. There are 5 orbitals for any L equal to 2. What is 2? The D subshell. There are 5 orbitals for the D subshell. We've already talked about that. Because you have 2 electrons and can occupy the, per orbital. 5 times 2 is 10. There's 10 elements across in the D subshell. L equal to 3. That's the F block. So we know there's 7 orbitals there, and there are 7 numbers here. Okay, representing 7 orbitals. And so I drew that out here. So we know the S has 1 orbital, P has 3, D has 5, and F has 7. How do we get that? If we look at the total number of electrons in the S subshell for color-coded periodic table, 2 divided by 2 is 1, 6 divided by 2 is 3, 10 divided by 2 is 5, 14 divided by 2 is 7. Okay, so they asked how many subshells, number of subshells, right? So there are 4 subshells, S, P, D, and F. Why? Because there are, for the L value, it's 3, 2, 1, 0. All right, so that's S, P, D, F. So 4 subshells, S, P, D, and F. So number of subshells, 4, S, P, D, and F. Number of orbitals in each subshell. So there's 1 orbital in S, 3 in P, 5 in D, 7 in F. So total number, you add those together, there are 16 orbitals total. 1 S orbital, 3 P orbitals, 5 D orbitals, and 7 F orbitals. You add those numbers together, you get 16 orbitals with a principal quantum number of 4. Okay. So we answered all 4 questions. We found L, we found M sub L, and then from that we could figure out, of course, number of subshells and number of orbitals in each subshell. All right. Going back to where we need to be here, starting a new section, electron configuration. So we're going to learn how to determine electron configuration of atoms at the ground state, which is basically the state at which the electrons are at their lowest energy levels, which those are unexcited electrons. Identify and explain exceptions to predicted electron configurations for atoms and ions. Okay, so there is a general way of figuring out the electron configuration for elements. Sometimes there are some exceptions. Okay, and those exceptions, unfortunately, there's no real easy way to be able to figure out what it is unless you just memorize it. Okay, so you're going to have some exceptions there. Relate electron configurations to element classifications in the periodic table. All right, so electron configurations. So we know that the energy of atomic orbitals increases as the principal quantum number n increases. As the principal quantum number n increases, the size of the orbital increases and the electrons spend more time farther from the nucleus. Thus, the attraction to the nucleus is weaker, and the energy associated with the orbital is higher and less stabilized, because the electrons basically are further away from the nucleus, they have less attraction, so they have higher energy. In an atom with two or more electrons, the repulsion between the electrons make energies of subshells with different values of L differ. So the energy of the orbitals increases within a shell in the order of S has less energy than P, which has less energy than D, which has less energy than F. Electrons and atoms tend to fill low energy orbitals first. Okay, so you can see that here. If you're trying to build an atom, for example, when you start to add electrons, you're going to add electrons. The first electron is going to go in the 1s orbital. Okay, it's going to have an energy level of 1. It's going to be in an s orbital, and so it's going to go there. The second electron, again, 1s. The third electron is going to go in the 2s. Okay, the fourth one in the 2s. The fifth one in the 2p. Okay, and keep going on until you fill that one up, and then you move on to 3s, and then 3p, and 4s. Okay, and so on. So here's a diagram that shows you the energy relationship between energy and the quantum number in subshells for each of the quantum number in subshell possibilities for the atoms. So with electron configuration, the arrangement of electrons in the orbitals of an atom is called the electron configuration of the atom. Electron configuration consists of symbols that contain three pieces of information: the principal quantum number, N, or the shell, the letter that designates the orbital type, L, a superscript number that designates the number of electrons in that particular shell. Okay. So here's electron configuration for hydrogen. The diagram for electron configuration specifies a subshell N and L value with letter, symbol, and superscript number is the number of electrons in that subshell. All right, so the electron configuration for hydrogen is 1s1. All right, so how do I get that? So let me quickly copy this so I can go back and forth. All right, so here you notice that hydrogen's the 1s. Here it's 1s, and there's only one electron in that subshell, so its electron configuration is 1s1. Let's do the next one, helium. All right, so helium, let's see here. Helium is on the first energy row, okay, and it has 2 electrons. So here I'm going to make a little list here in just a minute. So to show you, this very redundant. Okay, so all right, so element hydrogen, its electron configuration is 1s1. So if we look here, how did I get that? It's on the first energy level. It's color-coded S. So that first electron is in the S subshell, and there's 1 electron. So its electron configuration is 1s1. For helium, how do I figure out its electron configuration? Well, if I look at my periodic table, it's going to be 1s, and then there are going to be 2 electrons. The first electron, though, is going to be in the same spacing as hydrogen's, and the second electron is going to be the second electron in the 1s orbital. So electron configuration for helium is 1s2. There are 2 electrons, because helium has 2 electrons. Hydrogen, there's only 1. Okay. What about the next element, lithium? So lithium's here, right? But it has 3 electrons, but its first 2 electrons are the same as that if it were helium. So that means that its electron configuration is going to be 1s2, 2s1. 2 because this third electron's on the second energy level, and there's 1 there. Okay, so that's why you get 1. So it's going to be 1s2 and then 2s1. So the third electron goes in the second energy level in an S subshell. And that's what's color-coded here on your periodic table. It tells you that 2, and then it's color-coded S. Okay, by the way, this periodic table is color-coded. It tells you the subshells here. So these are S, and these are Ds, yellow is D, red is P, and green is F. All right, so let's do one that's more complicated. What about oxygen? All right, so oxygen has, let's see, it has 4, 5, 6, 7, it has 8 electrons. All right, so its first 2 electrons, though, are going to be just like that of helium. So it's going to be 1s2. Okay. So for oxygen, it's going to be 1s2. That's the first 2 electrons. And then the second 2 is 2s2, right? 2s2. Go back here. So 2s2. So now we have 4 electrons. We need 4 more. And then 2p, 1, 2, 3, 4. So oxygen, you see how there's 1, 2, 3, 4, 4 electrons in the 2p subshell. So it's going to be 2p4. 2p4. If I add up my superscripts here, 2 plus 2 plus 4, that's 8 electrons. So one way to double check yourself is making sure, you should have 8 electrons. Here, and I do. Here I should have 3 electrons, and I do. Here I should have 2, and there I should have 1. So you can double check by adding up your superscripts. All right, let's do another couple here. Let's do potassium. Okay, what is the electron configuration for potassium? All right, so for potassium, if I look at my periodic table, it's going to be 1s2, 1s2, 2s2, 2p6, all right, 3s2, 3p6, okay, and then 4s1. Why 4s1? Here I'm stopping at potassium, right? I'm starting with hydrogen and going all the way through, okay, until I get to potassium, 4s1. Okay, so let's see, with potassium, if I add up all the superscripts I should have and the number of electrons associated with potassium, let's see, 12, 19 electrons is what I count. So you don't have to count, this is just a way to double check. But anyways, the way you go about this is just starting with hydrogen, you go all the way through, you're counting. You're going the order in which you're looking at the atomic numbers, 1, 2, 3, 4, all the way until you get to the point where you're stopping at the element that you're interested in. Okay. Now, let me do one like in the D block, because this D block is different in that students forget that the energy level is 3 here and not 4. All right, so I want to find the electron configuration for iron. So that would be 1s2. Notice how it's all the same. 2s2, 2p6, 3s2, 3p6, 4s2, and then look, 3d6. Okay, so this is the electron configuration for iron. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So you can notice how I went from 4 and then went down to 3 because it's D, And then if it went up to P, if I had to go through P, it would go up to 4 again. Okay, so again, when you're looking at your energy values, your quantum numbers here, remember that D doesn't line up exactly right. Okay, it's different. All right. So the Aufbau principle, we're talking about basically building up to a point where you're adding up all your electrons. So to determine the electron configuration for an atom, we need to add up the number of electrons equal to its atomic number. Beginning with hydrogen and continuing across the periods of the periodic table, we add 1 electron to the subshell of the lowest available energy first, and then we keep going and we add up our electrons that way. This procedure was called the Aufbau principle, from the German word meaning to build up. When writing electron configurations and orbital diagrams, keep in mind the Pauli exclusion principle, and that you only have a maximum of 2 electrons per orbital. All right, so notice this diagram depicts the energy orbital for atomic orbitals and is useful for deriving ground state electron configurations. So you can figure this out by just looking at your periodic table. Like if you start with, you're always starting with hydrogen, right? So hydrogen's 1s, so that's where you have to go through first. And then 2s, and then 2p. You see that? 2s, and then 2p. Okay. Then 3s, and then 3p. 3s, 3p. And then 3d. 4s, 4p, 4d. 4f, 5s, 5p, 5d, 5f, and so on. Okay. And then look how it goes back down. So it goes to 5f, and then let's do that. So 5f is here. And then it goes S, 6s, 6p, 6d, and then 7s, 7p. So it goes to max here with f's, and then it goes back down, whittles back down. And so 8s, which isn't on the periodic table yet, but it should only have 1 s. If this trend, because you can see the trend how it winds out and it comes back down in terms of number of subshells for each energy level. All right, so we've seen this before. This is a color-coded periodic table. I would suggest you use this when you're trying to figure out electron configurations. It's color-coded. It tells you the energy levels, okay, and it tells you the subshells, and it's color-coded based off subshells. And that's really important to use this when you're learning electron configurations. All right, electron configuration, orbital diagram. So what's an orbital diagram? It gives you a little bit more information, okay? The way I like to teach orbital diagrams is start off by writing an electron configuration, which is what they did here. And then you go one step further and you're showing the electron the m sub s value by showing the spin, okay? The spin is represented by an arrow. So this is like a lazy way to write an arrow going up. Okay, so orbital diagrams are pictorial representations of electron configurations showing the individual orbitals and the pairing arrangement of the electrons. So here we have the electron configuration for hydrogen, 1s1. Its orbital diagram, this box represents the orbital. In this orbital box, there's one arrow pointing up, meaning there's 1 electron. This arrow represents the electron having a positive 1/2 spin, okay, or m sub s value of plus 1/2. A down arrow, downward pointed arrow, would indicate m sub s value of negative 1/2. So here for helium, its electron configuration is 1s2. So I would write the electron configuration, and then I write the energy level in the subshell down below the box, and then it has 2 electrons and 1s, so I put arrow up, arrow down. You see how they did the lazy arrow because it's easier to fit, I guess, arrow this way than it is to write them. It just doesn't take as much space, I guess, is what I'm trying to say. All right, so electron configuration for lithium, 1s2, 2s1. Again, you can see the 2 electrons in the 1s orbital, and there's 1 electron in the 2s orbital. For beryllium, 1s2, 2s2. See how the boxes are put in such a way. All right, for boron, its electron configuration, 1s2, 2s2, 2p1. So here in the 1s, I have 2 electrons or 2 arrows, each arrow pointing in the opposite direction. 2s2, again, 2 arrows. 2p1, so notice I have 3 boxes. They're all at the same energy level, so they're written side by side. And we have 1 electron here in a 2p orbital. All right, so when you're doing orbital diagrams, the only real way to mess things up is to forget about Hund's rule. So Hund's rule states the lowest energy configuration for an atom with electrons within a set of degenerate orbitals is that having the maximum number of unpaired electrons. So here, for example, the electron configuration for carbon is 1s2, 2s2, 2p2. So you might think, well, okay, so I have 2 electrons in a 1s orbital, 2 electrons in a 2s orbital, and then I need 2 electrons in a 2p orbital. So I'll just put arrow up, arrow down. So with Hund's rule, it says that you have to fill the orbitals halfway. So it says the lowest energy configuration for an atom with electrons within a set of degenerate orbitals. That means the orbitals have the same energy values, which all these 2p orbitals do, is having the maximum number of unpaired electrons. So what that means is, instead of putting arrow up, arrow down, we want to put arrow up each time. We want to fill up that orbital halfway. And a good way to remember that is this. If you think of an orbital as an apartment, would you like to have a roommate, or would you like to have your apartment all by yourself? So you would probably like to have an apartment all by yourself. Electrons are the same way. They don't want to have to share the same orbital. Okay? So if there's an open apartment or orbital, they're going to occupy that one before they go back and have a roommate and have to occupy it with someone else or some other electron. So that's the case here. So if I have to add another electron, since these orbitals are all degenerate, they're all the same energy values. Again, I would add another electron with an arrow pointing up, indicating that you're going to fill up the orbitals halfway first. And then if I have to add another electron, then I'll go back and pair it, okay? But with degenerate orbitals, and those are orbitals like p, d, and f, you fill them up halfway first. And then if you have to go back and pair up your electrons and the orbitals, then you do. Okay, so here's a good representation of that. We see with nitrogen, we add another electron there, so we filled it up halfway first. And then with oxygen, we end up having to add another electron, so then we have to pair it up there. And then a second electron, we have to pair it here. And then another electron, then it's completely full.